Right, lecture 12, the benefits of food processing. Completing the food processing series. We are how we eat. Interesting question. Look at the benefits of cooking. Remind ourselves a little bit about food consumption habits changing. Look at preservation, and then look at issues around anti-nutritional factors, in particular protease inhibitors. Okay, so our cousins, the chimpanzees, spend most of their day chewing tough food, very strong jaw muscles, take up a large part of their head and seem to have prevented their brain cases from growing larger. Somewhere in our hominid line, our ancestors developed tools for cutting, slicing and grinding food. This reduced the need for chewing and it seems allows us to develop larger brains. Slicing and dicing made us human is a reasonable hypothesis. Reducing the need to chew by about 17%. And then there's cooking. Okay, so I should have brought that image in. This paper, which you link through to summarises the hypotheses, suggests that cooking has many benefits, including making food safe to eat, of course, reducing chewing and releasing more nutrients, and there's certainly good evidence for most of these things. This EUFIC resource on food processing is well worth having a look at. Reviews the main benefits, which is an examinable topic. Of course, all of this is examinable. The methods involved, looks at a range of new technology approaches, the effects of processing on nutritional quality, which can sometimes be negative but sometimes can be positive, and the importance of processed foods in our modern societies, which is something which is often overlooked. So well worth having a read through that resource. We've looked at the Maillard reaction in terms of benefits and also some downsides earlier. We're talking more here about proteolysis. Proteolysis is the hydrolysis of proteins into smaller peptides and amino acids, making them more easily digestible. Cooking will do this and makes the nutrients much more biologically available than in uncooked meat or uncooked food in general. Yeah, okay, so some preserved methods. We'll bring up a graph here. Yeah, okay, this graph is a little bit dubious. It involves some natural products like fruits and processed ones like paste, so maybe they should have been on separate graphs. Nevertheless, it clearly illustrates if you want a good amount of the carotenoid lycopene, the best sources are ketchup and paste. There's good evidence that lycopene in the diet reduces the risk of age-related macular degeneration and may have other benefits. And in terms of AMD, may reverse the condition in some cases. If you haven't heard of it, AMD is a common condition that affects the middle part of the vision. Usually first affects people in the 50s and 60s. It doesn't cause total blindness, it can make everyday activities like reading and recognising faces difficult. Obviously, going back to this image over here, preserving food by freezing or tinning can help preserve micronutrients, so it's important to the health of populations. Yeah, some more lycopene data. Notice how variable amounts are. Different products will have different amounts of tomato and different processing methods may be involved. Ketchup wins in terms of lycopene, but may be high in sugar, of course. It's not really a surprise that raw tomatoes are the lowest. They have a much higher water concentration than the processed products. Yeah, we may have seen this before, an interactive graph of changing UK food habits. I'll open it up and we'll have a brief look at it, but you'll look at it in your own time. Okay, so I'm sure we've seen this before. There's a graph I did a while back looking at changing patterns in the UK diet based on the calories of the Eat Well plate effectively. We can take everything off. We can have a look at how beverages have changed. So the bottom line is a decreasing consumption of tea and a steady increase of coffee, but still quite slow. They've probably narrowed. This is a bit out of date now. I need to update this, but I haven't really had the time. It's about 10 years out of date, so I suspect these lines may have crossed by now. And this doesn't include things like fruit teas, of course, which have been growing in popularity in recent years. So again, you can have a look at this yourself. You can have a look at things that are high in fat and sugar, for example. See how it changed. So we see there sugar as a whole went up. It was quite low at the end of the Second World War because it was under rationing. Then when it came off rations, it went up. A lot of people baked at home. And it's gone down and continue to go down. Again, it'll be interesting to see what the effect of recent media interest in bacon will have on this. Okay, so we'll just get rid of that. Moving out of the way. Right, so preservation of food, which we've mentioned a little bit earlier on. Bring these in. 20 years ago, there was nothing like the choice of fruits we see these days, and we see them all year round. Back in the day, when I was a child, children used to get an orange in their Christmas stocking. It was probably the first one they had seen for several months. We've got a picture there of a sliced and diced fruit, and we talked about this when we discussed the inhibition of PBO and the use of modified atmosphere packaging in earlier lectures. The food preservation methods shown here, drying, using sugar, perhaps making cheese, salting, smoking, have been around for thousands of years. They generally work by lowering the water activity of the food, again discussed in an earlier lecture. Again, some reminders from the earlier lecture on water activity. Well, worth maybe thinking about linking these ideas together. Okay, so canned or tinned food. Nicolas de Pertz was a French chef, confectioner and distiller who invented the method of preserving food by enclosing it in hermetically sealed containers, which includes glass jars and tins. Using corked glass containers reinforced with wire and sealing wax, he kept in boiling water for various lengths of time. He preserved soups, fruits, vegetables, juices, dairy products, marmalades, jellies and syrups. This was during the Napoleonic Wars when France was blockaded by the Royal Navy, and he was awarded a 12,000 franc award in 1810, which he used to set up the first commercial canning plant. And there's a link there if you want to read more about the Pertz. Unlike, say, Colonel Sanders, Clarence Birdseye was a real person. He was an American businessman and inventor best known for developing a process for freezing foods in small packages suitable for retailing, which I think it's fair has revolutionised the retailing of food. Freezing of food, of course, has been a major factor in improving food safety, which you've covered in the food safety module. You've covered the temperature zones. Okay, anti-nutritional factors. Cooking has a downside in some specific cases, and also what we're talking about more here is the fact that some foods contain what we refer to as anti-nutritional factors, and we'll explain what they are in a second. Start by talking about protease inhibitors. As mentioned earlier, proteases are enzymes that hydrolyze protein ultimately into amino acids, so they're part of their digestive protein process. So you have pepsin, for example, in your stomach, which is a proteolytic enzyme. One important class of anti-nutritional factors are protease inhibitors. As the name suggests, they inhibit the actions of proteases. Protease inhibitors have been found in a great variety of plants, including most legumes and cereals and certain fruits, vegetables as well. They may resist proteolysis themselves to different degrees and retain this ability during digestion. They're also often quite resistant, as we'll see, to temperature, which means that they sort of hang around the inhibitors longer than the proteins going through the digestive system. So there can be a problem. Moving on. These are the main characteristics and potential negative impacts of protease inhibitors. You can read them yourselves. As mentioned earlier on, these enzymes are all over the place. They're widely distributed in nearly all plants, animals and microorganisms, where they have many, many roles. What we're concerned about here is their potential anti-nutritional effects. The legumes. The legume family consists of plants that produce a pod with seeds inside. The term legume is used to describe the seeds of these plants. Common edible legumes include lentils, peas, chickpeas, beans, soybeans and peanuts. And there's a link there to Science Direct, which has a collection of papers on trypsin inhibitors if you're interested in. Trypsin is one of the most important ones in terms of inhibition. So legumes have natural components such as lectins, amylase and trypsin inhibitors, which may adversely affect their nutritional properties. But proper cooking and treatment will remove most of these issues. So you're well aware that in many cases people are well aware that with raw beans you've got to soak them and you've got to steep, then you've got to simmer them for quite a while. Otherwise, Yeah, okay, bringing the picture of the cooked beans there. So they've obviously been treated and been pre-treated, so effectively ready to eat when you open the tin. Soybeans produce a range of protease inhibitors, including trypsin and chymotrypsin, including 4-trypsin and chymotrypsin. They can be made safe by soaking overnight and then simmering for 1 hour, which deactivates and inactivates the proteases. It probably denatures a lot of the proteins as well, of course. In principle, we get quite a lot of protein inhibitors from our diet, and probably more so for vegetarians and vegans. I don't know if anyone's looked at whether this is a significant issue in that context. Okay, so classes of protease inhibitors. There are two main classes in legumes. The Kunitz PIs have a single inhibitor site, where the Baum and Burke ones have two and are said to be double-headed. As well as legumes, they're also found in cereals such as wheat, which is why we saw a picture of wheat a little bit earlier on. And there's a link there to some information about the genetics if you're interested. Just for fun and not examinable, a map of a Kunitz soybean trypsin inhibitor. Note the single inhibitor site in this one, so located in between amino acid residues 63 and 64, which I'm now looking for. And can't quite track down where it's like following a little maze, so around this area. Again, just for fun, the Baum and Burke inhibitor has two sites, and here they are, clearly identified here and here. This is quite heat stable, maybe due to the folded structure of the protein being primarily held together by disulfide bonds, which are these things. These are strong covalent bonds, rather than many proteins which are stabilized by weak hydrogen bonds, and this may contribute to the heat stability of this particular inhibitor. So, a summary of the characteristics of the two protease inhibitor groups. Again, note their stability to heat and digestive enzymes, and as long as they are active, protein digestion may be inhibited. This is how to inactivate them. I'm not going to read through this, you can do it yourself. So in summary, the problem is often inadequate cooking. Okay, there's an acronym there, TIA, trypsin inhibitor activity, so a measurement of how active the inhibitors are. So we've looked at this both in terms of polyphenol oxidase and in terms of alkaline phosphatase in the human metabolism module. Okay, start off with another definition then, a zymogen, an inactive substance which is converted to an enzyme when activated by another enzyme. In many cases, for proteins, we don't have little stocks of them ready. We either have to synthesize them de novo from scratch or from precursors, which is what we're talking about here. The efficient digestion of proteins in the digestive system requires the action of a number of proteolytic enzymes, each hydrolyzing peptide chains at specific points. These enzymes are produced and stored in the pancreas in a precursor form known as zymogens. The efficient digestion of proteins requires simultaneous activation of all of the zymogens, and trypsin is thought to be a common activator of many pancreatic zymogens, so if it's inactivated, it can have downstream problems, is the point about this. Yeah, so some evidence based from animal studies on the potential effect of protease inhibitors. Obviously, it's sometimes difficult to extrapolate from animal studies to human studies, but it seems reasonable to assume there are issues, and we do know this from population studies, and there are some quite serious issues associated with protease inhibitors. It can also have toxicological effects. These are thought to be the ways in which protease inhibitors can have specific toxicology effects, as well as inhibiting the digestion of proteins. As usual, again, we have our caveat that it's not possible to extrapolate always directly from animal studies to human studies, but there are reasonable reasons for concern here. Here's a term which you may have come across, protein energy malnutrition. PM is sometimes called protein energy undernutrition these days. This is an energy deficit due to the deficiency of all macronutrients. It commonly includes deficiencies of many macronutrients. It can be sudden or total due to starvation or gradual. Severity ranges from subclinical deficiencies to obvious wasting, with things like edema, hair loss and skin atrophy, to starvation. Multiple organ systems are often impaired. These are the main categories of the condition. See this link down here from MSD for a summary of the conditions. We'll notice that they are caused by protein energy and energy deficiency. So again, if proteins aren't digested properly for reasons such as the ones we've talked about, they can contribute to these quite distressing conditions. And there's a map of protein energy metabolism issues around the world. The darker the colour is, the more significant the issues are. Okay, and that's all for that. Thanks for listening.